We're on to the very last step of the completeness theorem proof now. Here's what we've done so far. We've built a maximal consistent SD set gamma infinity, and then we established the regularity lemma, which told us that being a member of gamma infinity is just like being true on a truth assignment. Remember that ultimately the claim we're trying to prove is a variation of the completeness theorem that says that if a set of sentences gamma is consistent in SD, then it's truth functionally consistent. Okay, so that's a claim that ties together consistency in SD with truth value assignments. Okay, and that is what we're going to prove today. So today in this video, we're doing everything today, but in this video, we're going to prove by induction that every sentence of SL is going to be true on a truth assignment if and only if it's a member of gamma infinity. Okay, so here we have a claim about consistency in SD, namely being a member of gamma infinity, which is by definition a set that's maximal consistent in SD, and we have here a claim about truth value assignments. Okay, so we're finally going to be able to prove that claim. We're going to call the truth assignment that we're dealing with A star, just for clarity, so that's just what we're going to be calling the truth assignment. Okay, so to begin our proof, we're just going to stipulate that every sentence letter in gamma infinity is true and every negated sentence letter is false. Okay, so we're mostly going to be working with the compound sentences, and we're just going to accept by stipulation that the sentence letters are true and that the negated sentence letters are false. This is a proof by induction, so we're going to go ahead and do the 3 steps of proofs by induction that we're familiar with. So for the base case, we want to prove that the claim we're proving holds for the most basic case possible. We're going to be doing an induction on the number of connectives in a sentence. So we're doing sorry, I don't know what happened there. We're doing an induction on the number of connectives in a sentence. Okay, so what is the most basic case? Well, a sentence of SL can have 0 connectives, right? And in that case, it's just a sentence letter. So our base case is going to be n equals 0, and we're dealing in that case with an atomic sentence. And we want to prove again that every atomic sentence, right, is true on a truth assignment if and only if it is a member of gamma infinity. Well, we stipulated that sentence letters in gamma infinity are true on the truth assignment, right? We did that by stipulation here. So we can say that by stipulation, every atomic sentence is true on a truth assignment A star, true on A star, if and only if it's a member of gamma infinity. Now we're going to move on to the induction hypothesis. So remember, in the induction hypothesis step of the proof by induction, you want to assume that the claim we're trying to prove holds for all of the things we're enumerating up until and including some number k. So again, we're doing an induction on the number of connectives in a sentence of SL. So let's phrase our induction hypothesis in this way. For every sentence P of SL with K or fewer connectives, the claim we're trying to prove holds. So P is true on A star if and only if P is a member of gamma infinity. Okay, so our induction hypothesis looks good. We're assuming that the claim we're trying to prove holds for everything up till and including K. All right, so now it's time for the induction step. So the induction step is then to prove that the claim we're trying to prove holds for k plus 1. So prove that a sentence of SL P with k plus 1 connectives is true on A star if and only if P is a member of gamma infinity. Okay, so there are 5 cases in the induction step because we need to do one case for each of the 5 logical connectives of SL. And we need to prove that no matter what connective of SL is the main logical connective of that sentence P with k plus 1 connectives is going to be true on A star if and only if P is a member of gamma infinity. Okay, so this, just like the last proof of the regularity lemma we did, we're proving a biconditional, right? There's an if and only if. So that means for each case, each of the 5 cases, for each of the 5 logical connectives of SL, we have to do 2 cases, one going in the right direction and one going in the left direction. But for both directions that we do, it's going to be the exact 3 same simple steps. These are quite simple and fun to do. So, buckle up. It's gonna be a fun ride. Okay. So the first step is to figure out what you know about the truth assignments and to write that all out. Okay, the second step is to apply the induction hypothesis. Okay, so we want to split up the problem, just as we've done with all proofs by induction in the induction step, split up the problem so that you can appeal to the induction hypothesis. And then, after you've done that, you can appeal to the regularity lemma. All right, so that might sound really weird and abstract, but it's going to become clearer once we do a couple of cases. Okay, so I'm going to do 2 cases with you. We're going to do the ampersand case and the material conditional case of this proof. One of the cases, actually I think 2 of the cases are on the problem set for this week. I think it's the disjunction case and the material biconditional case. But when you do those 2 cases, it's going to be the exact same 3 steps as we're doing here. Let's get started with the ampersand case. So we're going to prove that a sentence, let's say P equals Q and R. Okay, so we're replacing the P here with Q and R. Okay, so a sentence Q and R with K plus 1 connectives. Let me write with K plus 1 connectives is true on A star if and only if Q and R is a member of gamma infinity. All right, so we have 2 connections to prove. 2 directions to prove. So let's start out by doing this direction. So we want to assume that Q and R is true on A star. All right, so if Q and R is true on A star, then we know by the definition of the ampersand that Q is true on A star and R is true on A star. In order for a conjunction to be true, both of the conjuncts must be true. So we know this just by the truth table for the conjunction. Okay, but notice that Q and R both fall within the scope of the induction hypothesis because they each have fewer than K plus 1 connectives, right? If Q and R has K plus 1 connectives, then Q and R must both have fewer than K plus 1 connectives. Okay, so we can say that Q and R fall within the scope of the induction hypothesis. This is step 2 of the ones that I've written up here. Okay, sorry. So I'm jumping back and forth a bit. But what we did first was we figured out what we knew about the truth assignments on the basis of the truth table for the ampersand, right? And then we were in a position to apply the induction hypothesis because we know Q and R both have fewer than K plus 1 connectives. Okay, so once we know that Q is true on A star, we can know by the induction hypothesis that Q is a member of gamma infinity. Similarly, we know since R, we can apply the induction hypothesis on R. If R is true on A star, then it must be the case that R is true on R is a member of gamma infinity. Okay, so we now have these two facts. Q is a member of gamma infinity and R is a member of gamma infinity. And remember that we established in the regularity lemma that if we have both of these things in gamma infinity, then it must be the case that Q and R is in gamma infinity. And you can go back and check what we proved in the regularity lemma to verify that that's the case. But now we're on to step 3, where we appeal to the regularity lemma. So we're going to say, by the regularity lemma, therefore, Q and R is a member of gamma infinity. Okay, and that proves one direction. Okay, so we started out by just figuring out what we knew about the truth assignments of what we were working with that allowed us to appeal to the induction hypothesis. And finally, we appealed to the regularity lemma. So it's just the same 3 simple steps for each part of the proof. Okay, so now we're going to prove this direction. So to prove this direction, right, you might be thinking we should assume if Q and R is a member of gamma infinity, and then prove that Q and R is true on A star. But we're actually going to do it a little bit of a different way. So let's say that this biconditional up here is P if and only if Q. Right? When in our first case, we proved if P then Q, right? And you have to prove that it goes in both directions. So you might think that in the next step, we're going to be doing if Q then P. But actually, as I mentioned a couple of videos ago, if Q then P is just the same thing as if not P then not Q. Okay, and that's actually going to be what we're proving. We're not going to be proving that if Q and R is a member of gamma infinity, then Q and R is true on A star. Instead, we're going to be proving if Q and R is false on A star, then Q and R is not a member of gamma infinity. Okay, and that's the same thing. That's just proving this claim instead of this claim, but either way it works. Okay, so that's what we're going to be doing. So when we go in this direction, we're going to assume that Q and R is false on A star. And every time you do a case for one of the logical connectives, it's going to be the same thing. In the first scenario, you assume that the sentence is true, and in the second scenario, you assume that the sentence is false. Okay, so say that Q and R is false on A star. Then by the definition of the ampersand, we know that either Q is false on A star or R is false on A star. Okay, and again, we know that by just the definition of the ampersand. Okay, so on that case, by the induction hypothesis, so if Q is false on A star, then it must be the case that Q is not a member of gamma infinity. And we know that by the induction hypothesis, because Q and R both fall within the scope of the induction hypothesis. So Q is not a member of gamma infinity, or R is not a member of gamma infinity. Okay, so that completes step 2. So I'm going to scroll up here. So we figured out what we knew about the truth assignments, then we applied the induction hypothesis, and now it's time to apply the regularity lemma. So by the regularity lemma, right, since either Q is not a member of gamma infinity or R is not a member of gamma infinity, it cannot be the case that Q and R is a member of gamma infinity. Okay, not R, a member of gamma infinity. And you can look back to the regularity lemma to verify that, but this checks out by the regularity lemma. I'm getting a little sloppy. It's been a long day. Yeah, so you can go back to the regularity lemma to check that out. But here we've proven exactly what we set out to, right? We assumed that Q and R is false on A star, and we were able to prove first by appealing to the induction hypothesis, and second, by appealing to the regularity lemma that Q and R is not a member of gamma infinity. And that completes the conjunction case of this final step of the completeness theorem. So as I said before, we need to do one step for every logical connective. Two of them are on the problem set, but we're going to do one more together, and that's the case with the horseshoe. Okay, so we're going to now say that P is Q, if Q then R, where if Q then R has K plus 1 connectives, and we want to prove that if Q then R is true, if Q then R is true on a truth assignment A star, if and only if Q then R is a member of gamma infinity. Whew, all right, let's do this. So it's a biconditional, we have to do both directions. So let's do the right direction first. So we're going to say that if Q then R is true on A star. Okay, if Q then R is true on A star, then we know that either Q is false on A star or R is true on A star. And again, we know that just by the definition of the material conditional. Okay, so now we know that both Q and R fall within the scope of the induction hypothesis. I'll abbreviate that to IH. Okay, so both Q and R have fewer than K plus 1 connectives, so they fall within the induction hypothesis. So since we can apply the induction hypothesis here. So if Q is false, then that means that Q is not a member of gamma infinity by the induction hypothesis. Or if R is true on A star, then we know that R is a member of gamma infinity by the induction hypothesis. Okay, and now we can appeal to the regularity lemma. And again, you can go back and check what we proved last time in the regularity lemma. But if these two conditions are fulfilled, right, so either Q is not a member of gamma infinity or R is a member of gamma infinity, then we can conclude that if Q, then R is a member of gamma infinity. Okay, so we got to where we want to. We started by assuming that if Q then R is true on A star, and we proved that if that's the case, it must be that if Q then R is a member of gamma infinity. Time to go in the other direction now. So we're going to say that if Q then R is false on A star. Okay, so there's only one possible case, right, where if Q then R is false, and that's when Q is true and R is false. So that means that Q is true on A star and R is false on A star. And we know that just by the definition of the material conditional. Okay, so you can look back to the truth table to verify. Okay, so Q and R fall within the scope of the induction hypothesis. I'll abbreviate that again to IH. So because they fall within the scope of the induction hypothesis, we can transform this claim about being true on A star into a claim about membership in gamma infinity. So if Q is true on A star, then Q is a member of gamma infinity. And if R is false on A star, then R is not a member of gamma infinity. Okay, and then we can appeal to the regularity lemma to get to our conclusion that if Q is a member of gamma infinity and R is not a member of gamma infinity, then if Q, then R cannot be a member of gamma infinity. Okay, and that's it, right? We assumed that if Q then R is false on A star, and we showed that that entails that if Q then R is not a member of gamma infinity. And that concludes the horseshoe case for the proof of this final proof by induction. So once you've done all 5 connectives, then you will have proven the completeness theorem, okay? And that's really amazing. I can't believe that's it. It felt like it took forever. And you know what? It kind of did. And my mind is fried. And I don't think I'm making sense anymore. But I don't know about you. I had a great time. Let's pat ourselves on the back. We did it. Let me know if you have any questions. So as I said before, 2 of these cases are on the problem set for you to do.